Everything in the universe is on the move. Stars drift through the dark, galaxies spin in slow, endless spirals, and even the space between them is stretching wider every second. Our own planet, quiet under the night sky, travels through this vast ocean without pause. Nothing truly stands still, not you, not me, not even light itself. Tonight, let's take a gentle journey through the motions of the cosmos and see how everything, from dust to galaxies, finds its place in this grand flow. If you enjoy exploring the universe together, take a moment to like and subscribe. It helps us keep traveling through the stars, one quiet step at a time. For most of human history, people believed Earth was the center of everything. It seemed obvious. Each day they saw the sun rise, move across the sky, and set again. At night, the moon shone softly, and the stars looked fixed, like jewels spread across a dark sea. The sky appeared to turn, while the earth felt quiet and still. Across ancient cultures, from China to the Maya, this idea took hold. The heavens, they thought, revolved around us. In the Greek-speaking world, this belief grew into a detailed system thanks to a scholar named Claudius Ptolemy. He lived in Alexandria, Egypt, around the 2nd century CE, when Egypt was part of the Roman Empire. Ptolemy was not only an astronomer but also a mathematician and thinker who wanted to describe the heavens with care and order. He gathered knowledge from Babylonian star charts, Egyptian sky records, and Greek geometry, combining them into a grand design. He wrote his work in a book later known as the Almagest, which guided astronomers for more than 1,000 years. In Ptolemy's model, Earth sat motionless at the center of the universe. Around it moved the moon, the planets, the sun, and beyond them the stars fixed on a great outer shell. He imagined the cosmos as a series of clear spheres, each carrying one heavenly body and turning smoothly around Earth. To explain day and night, he said that the outer sphere of stars completed one full turn each day. He based this structure on a belief shared by many Greek thinkers that the circle was the most perfect shape, and therefore the heavens must move in perfect circles. But when astronomers watched the planets carefully, they noticed something strange. Sometimes a planet like Mars or Jupiter would slow down, stop, and even seem to move backward before continuing forward. This odd pattern, called retrograde motion, did not fit simple circular orbits. To explain it, Ptolemy added small circular paths called epicycles. Each planet moved along its own small circle, while that circle itself traveled around Earth on a larger one, called the deferent. This double motion could reproduce the backward steps seen in the sky. Even with epicycles, the motion still did not line up perfectly. So Ptolemy introduced another idea, the equant, an imaginary point slightly off-center from Earth. When viewed from this point, the planets seemed to move more evenly. His model became increasingly complex, filled with geometric details that helped it match observations better. Despite its flaws, it worked well enough to predict the movements of the sun, moon, and planets, and it became the foundation for calendars, navigation, and even astrology. For more than 1,000 years, people trusted this geocentric system as truth. Over time, though, cracks began to appear. The adjustments grew complicated, and some thinkers started to wonder whether a simpler explanation might exist. In 1543, a quiet challenge to Ptolemy's world appeared. A book called On the Revolutions of the Heavenly Spheres offered a different view. Its author, Nicolaus Copernicus, was a church priest from what is now Poland. In his time, most scholars studied within the church, which served as the main center of learning in Europe. Copernicus was trained in many fields: law, medicine, mathematics, but his heart belonged to the study of the stars. For years, he worked carefully, comparing records and running calculations. What he found changed everything. He proposed that the sun, not Earth, stood at the center of the universe. Earth, he said, was a planet, orbiting the sun once each year like Mars or Jupiter. He also described 3 kinds of motion for Earth. It spins once every 24 hours, explaining why the stars appear to rise and set. It travels around the sun yearly, causing the seasons and the shifting positions of the planets. And it slowly wobbles on its axis, a motion we now call precession. Copernicus did not guess. He built geometric models and used trigonometry to measure distances between planets and the Sunday. He noticed that the closer a planet was to the sun, the faster it appeared to move across the sky, exactly what his model predicted. Still, like Ptolemy, he believed planets moved in perfect circles. That kept his calculations from being fully accurate. Yet even with its flaws, his model offered something powerful, a new way to see the universe, not centered on us, but on the sun, with everything in motion together. The invention of the telescope opened a new way of seeing the universe. It began not in a grand observatory, but in the workshops of Dutch lens makers who joined pieces of glass for curious customers. Word of this strange device spread through Europe until it reached Italy, where Galileo Galilei saw its true potential. He did not invent the telescope, but he turned it into a scientific instrument. In 1609, he built his own and pointed it toward the night sky. What he found changed how humanity saw its place in the cosmos. When Galileo looked at the moon, he expected to see a smooth, perfect sphere, as tradition had long claimed. Instead, he found a world marked by mountains, valleys, and deep craters casting long shadows. The moon was not a flawless light in the heavens. It was solid and uneven, like Earth itself. Then he turned his telescope toward Jupiter and saw 4 small points of light nearby. They shifted position night after night, never wandering far. Galileo realized they were moons circling Jupiter. This was proof that not everything revolved around Earth. A planet could hold its own system of moving bodies. Galileo's next target was Venus, a bright world that changes shape as it shines in the sky. Through his telescope, he saw that Venus went through phases, just like the moon, sometimes full, sometimes a thin crescent. This could only happen if Venus orbited the sun, not Earth. The pattern matched perfectly with Copernicus's model, and it showed that the sun sat at the center of the system. Galileo's simple tube of glass had revealed what no one could deny. Earth was not the still heart of creation. While Galileo showed the world new sights, another mind worked to uncover the laws behind the motion. Johannes Kepler, a German mathematician and astronomer, inherited years of careful planetary observations from his teacher, Tycho Brahe. Tycho had measured the heavens without a telescope, building huge instruments and recording the movements of the planets with great precision. Though Tycho doubted the sun-centered system, his data became the foundation for Kepler's discoveries. Kepler focused on Mars, a planet whose motion often broke the rules of circular paths. For years, he tried to fit its movements into perfect circles, as many believed the heavens demanded, but the numbers would not cooperate. Finally, Kepler let the data lead him. The pattern that emerged was elegant, but unexpected. The planets move not in circles, but in stretched ovals called ellipses. This became his first law of planetary motion. Each planet travels in an ellipse, with the sun resting off-center at one focus. As Kepler studied further, he found another rule. Planets speed up when they are closer to the sun and slow down when they move farther away, yet they sweep out equal areas in equal times. This became his second law, describing a steady rhythm of motion that matched the precision of Tycho's records. His third law linked time and distance, showing that the farther a planet is from the sun, the longer it takes to complete its orbit. These three laws described the quiet order of the solar system with mathematical grace. Together, Galileo's telescope and Kepler's equations gave humanity new eyes and a new language to describe the universe. Yet one question still waited. Why did the planets move at all? What invisible hand guided their paths through space? That answer came with Isaac Newton. Legend says he began thinking about gravity after watching an apple fall, but what mattered was his insight that the same force pulling an apple to the ground also kept the moon in its orbit and the planets circling the Sunday. Newton's law of universal gravitation showed that every object with mass attracts every other object, and that the strength of this pull depends on distance and weight. With this, he united the physics of Earth and the heavens under a single rule. Using Newton's equations, scientists could calculate the motion of planets. Earth travels around the sun at about 30 kilometers per second. Mercury, closer to the sun, moves faster. Mars, farther out, moves more slowly. The balance of these speeds keeps each world in its path. For the first time, the cosmos followed one clear, universal logic. But even this harmony carried a quiet surprise. When astronomers looked deeper, they found that the sun itself was not fixed. It too was moving, drawn forward on its own long journey through the Milky Way, part of a motion that extends far beyond the boundaries of our solar system. For centuries, people had pictured the sun as the solid anchor of the heavens, the fixed center around which everything else turned. But even the sun was not still. It too was part of a larger motion, carried along on a vast cosmic journey. The Copernican revolution had changed everything. Earth was no longer the center of creation, but a moving world circling the Sunday. This shift reshaped not only astronomy, but also humanity's sense of place. Once the new model settled into people's minds, the sun became the new foundation of stability, the bright center of the universe itself. For a time, that picture held firm. In the 18th century, a man who began life as a musician would quietly overturn it again. William Herschel was born in Germany in 1738 and moved to England to compose music. Yet in his spare time, he became fascinated by telescopes. He taught himself to grind mirrors and build lenses, designing instruments so advanced that they rivaled the finest in Europe. Night after night, he turned them to the sky, recording what he saw with patient care. His goal was simple, but daring to find out whether the countless stars above were scattered without order or formed part of a grand structure. With his sister Caroline at his side, Herschel began counting stars in narrow slices of the sky. He tallied them by number and position, strip by strip, until a pattern appeared. More stars seemed to cluster along a faint band that stretched across the heavens, the Milky Way. From his careful notes, Herschel sketched a shape, a broad, flattened disk filled with stars, like a great wheel. At its center, he placed the Sunday, He could not have known that clouds of interstellar dust were hiding the most distant stars, making the universe appear smaller than it truly was. Still, his conclusion was remarkable for the time. He had revealed that the stars belonged to a single system, the galactic system, and that our sun was part of it, not beyond it. Herschel sometimes saw soft patches of light that he called nebulae. He believed they were clusters of distant stars, though he did not realize they were entire galaxies far beyond the Milky Way. Even without that knowledge, his work was groundbreaking. Humanity had lost not only its central place in the solar system, but also its central place in the galaxy. His flattened map of stars carried a quiet truth. If the Milky Way had shape and structure, it must also have motion. And if it had motion, then so must the sun and earth within it. This idea led to a new question that haunted astronomers. How can we tell what is truly moving when we ourselves are always in motion? Every observation of the universe is made from Earth, a planet spinning and circling the sun, which itself may be drifting through space. The answer lies in what scientists call a frame of reference, the point from which motion is measured. Imagine sitting inside a train. Everything around you feels calm. A cup of coffee rests steadily in your hand. Outside the window, another train slides by. And for a moment, it seems that the other train is moving backward. But without seeing the ground, you cannot be sure. To you, everything feels still. To someone on the platform, you're rushing past. Both are true, because motion depends on perspective. The same principle holds for the universe. Movement is always relative. In the late 19th century, a quiet Dutch astronomer named Jacobus Kapteyn took up this problem. He lived in an age when Herschel's maps were long accepted, but the Milky Way's true shape and motion were still unknown. Kapteyn did not seek fame. He preferred precision. He gathered data from observatories across the world, from South Africa to Argentina to Australia, measuring not just the brightness and position of stars, but also their proper motion, the tiny shifts in their positions that occur over years. After decades of patient work, a pattern emerged. The stars were not moving randomly. They seemed to form two great streams crossing the heavens, like vast currents of light. At first, this appeared to mean the stars themselves were rotating in opposite directions. But Kapteyn saw something deeper. The pattern was an illusion caused by our own motion. Like a person walking through a crowd, it was we who were moving while others seemed to float past. When Kapteyn applied his calculations, everything fit. The sun, along with its planets, was drifting steadily through space toward a point in the constellation Hercules. This path became known as the solar apex. The speed was about 20 kilometers per second, a calm but unstoppable glide through the Milky Way. The sun was no longer a still beacon. It was a traveler. Kapteyn wanted to go further. If the sun moved through the galaxy, then what was the shape of the system it belonged to? Using his data on stellar motions and brightness, he built the first model of the Milky Way, a great, flattened disk about 40,000 light-years across, with the sun near the center. Later, astronomers would find that his model was too small, limited by dust that hid the farthest stars, but the achievement was profound. From faint motions and small shifts of light, Kapteyn had drawn the first map of our galaxy, showing that even the sun, once thought unmoving, was just one traveler among billions. The question of motion did not end with the sun's steady drift through the Milky Way. Once astronomers learned that our star was moving, a deeper mystery came into view. For generations, people had noticed faint, hazy patches scattered among the stars. They were called spiral nebulae, and most thought they were small gas clouds or clusters within the Milky Way itself. but others wondered if they might be far more distant, perhaps whole systems of stars, other galaxies beyond our own. That debate would change everything. In the early 20th century, Edwin Hubble worked with the Hooker telescope on Mount Wilson in California, then the largest telescope in the world. In 1923, he turned its great mirror toward the Andromeda Nebula, one of those bright spirals. Among its countless stars, he spotted a special kind of variable star, a Cepheid. These stars pulse in brightness in a steady rhythm, and thanks to the work of astronomer Henrietta Swan Leavitt, their pulsation period could be used to calculate distance. When Hubble made his measurements, he found Andromeda was millions of light years away, far beyond the edge of the Milky Way. The meaning was staggering. Andromeda was not a small cloud inside our galaxy, but a galaxy of its own, filled with billions of stars. The universe had expanded overnight, not in size, but in our understanding. The Milky Way was no longer the entire cosmos, but one island among countless others, scattered through a vast ocean of space. This discovery offered astronomers something they had never had before: perspective. Living inside the Milky Way makes it impossible to see its full form, just as a person standing among trees cannot easily picture the forest's shape. By studying other galaxies, scientists began to piece together the structure of our own. Many appeared to have spiral arms, glowing centers, and thin disks of rotating stars. By comparison, they could infer that our Milky Way shared the same grand design. Through the mid-20th century, new tools deepened this picture. Radio astronomy allowed scientists to peer through the thick clouds of interstellar dust that blocked visible light. They traced the faint radio signals from hydrogen atoms to map the spiral arms that wind around the galactic center. It was a slow, patient effort, building a model of the Milky Way from within. Among those who advanced this understanding was the Dutch astronomer Jan Oort. Studying the motion of nearby stars, he realized the galaxy did not rotate like a solid wheel. In a wheel, all parts turned together, but the Milky Way moved more like a whirlpool, inner stars circling faster than those farther out. Oort developed equations, now called the Oort constants, that described this uneven rotation. From his work, he calculated that the sun lies about 30,000 light years from the center and travels around it at more than 200 kilometers per second. At that pace, the sun takes roughly 225 million years to complete one galactic orbit a single galactic year. Every star visible in the night sky makes the same long journey, orbiting the unseen heart of our galaxy. The question then turned to that hidden center. What was strong enough to hold billions of stars in orbit? Radio telescopes offered a clue. Hydrogen signals revealed that stars and gas clouds moved faster near the core than expected, as if pulled by something massive and invisible. Later, with the help of a powerful network called the Very Long Baseline Array, 10 radio antennas linked across thousands of kilometers, astronomers could measure tiny movements across the sky with exquisite precision. They tracked natural radio beacons known as masers, bright bursts of microwave energy around newborn stars, and used them as fixed points to map motion through the galaxy. Combining these measurements built a three-dimensional picture of the Milky Way. Stars traced long spiral paths, twisted by gravity, and at the center of this vast pattern lay something extraordinary, a compact, bright radio source in the direction of Sagittarius. It moved stars at incredible speeds, but no visible object was there. The only possible explanation was a supermassive black hole containing more than 4 million times the mass of the Sun, yet confined within a region smaller than Mercury's orbit. This object, now known as Sagittarius A asterisk, anchors the Milky Way's structure and keeps its stars bound in their endless orbits. Even so, the galaxy is not fixed or still. It ripples and bends as it spins, its arms lifting and dipping like waves on a cosmic sea. The part of the galaxy where our solar system lies, the Orion Spur, rises gently above the galactic plane and then sinks again, following that slow rhythm. And all of it, the sun, the planets, and every star we can see, drifts together through space, carried forward in the Milky Way's long, graceful voyage across the universe. By the early 1900s, astronomers had found a new way to measure motion in the universe. When a star or galaxy moves toward us, its light waves compress, shifting slightly toward the blue end of the spectrum, a blue shift. When it moves away, the waves stretch, shifting toward red, called a red shift. These tiny color changes became a way to read cosmic motion. Edwin Hubble used this method to explore distant galaxies, and what he found transformed our understanding of the cosmos. Most galaxies, he discovered, were not standing still. They were racing away from us, and the farther they were, the faster they moved. The pattern was clear. Distance and speed were linked. The only possible explanation was that space itself was expanding, carrying galaxies outward like raisins in rising dough. This single insight revealed that the universe had a beginning, a time when everything was closer together and laid the foundation for what we now call the Big Bang. Yet, not all galaxies were retreating. One in particular seemed to be heading the other way, Andromeda. In 1912, astronomer Vesto Melvin Slipher studied Andromeda's light and found it was blue shifted, meaning it was moving toward us. At the time, few understood what that could mean. A century later, with powerful telescopes and precise measurements from missions like Gaia and the Hubble Space Telescope, astronomers could finally map its motion in full detail. The result was unmistakable. Andromeda is not drifting harmlessly nearby, it's on a direct path toward the Milky Way. The two galaxies are closing the gap at about 500 kilometers per second. Even so, the distance between them is enormous, roughly 2.5 million light years, or about 24 quintillion kilometers. At that rate, their first meeting will happen around 4 to 5 billion years from now. It's easy to imagine such a collision as a fiery catastrophe, but reality is far calmer. Galaxies are mostly empty space. The average distance between stars in our region of the Milky Way is around 4 to 5 light years, tens of trillions of kilometers. If each star were the size of a ping pong ball, the next one would be hundreds of kilometers away. When the Milky Way and Andromeda finally merge, nearly all stars will pass by each other untouched, gliding through the darkness in silent motion. Still, gravity will make the encounter spectacular in its own way. Some stars near the crowded centers may collide, while others at the edges will be thrown out into intergalactic space. The true drama will unfold as gravity stretches and reshapes both galaxies. Their spiral arms will twist and tear apart, long streams of stars flung outward like ribbons. Over the next 1 billion or 2 years, they will spiral together, merging into a single, massive elliptical galaxy already named Milkomeda. It will shine brighter and appear rounder than either galaxy today, a great glowing sphere of stars and dust. Our sun, if it still exists, may drift into a new orbit, carried farther from the center and wandering through the transformed galaxy. The universe, as always, will keep moving forward, its quiet dance of creation and change continuing, one graceful turn after another. Even the coming union of the Milky Way and Andromeda is only a small part of a greater story. Our galaxy is not drifting alone through space, but moving within a vast network of galaxies bound by gravity. To see the full picture, we have to step back, past the Sun, past the Milky Way, past even the familiar cluster of galaxies that surround us. The universe is not random. It is shaped by gravity into great patterns, like rivers of matter flowing across the landscape of space. The Milky Way belongs to a small family called the Local Group, a collection of about 80 galaxies spread across 10 million light-years. The two giants, our Milky Way and Andromeda, each hold smaller companions. Around the Milky Way, the large and small Magellanic Clouds glide like faint satellites. Andromeda, too, carries its own followers, such as Messier 32 and Messier 110. Yet this family is only one neighborhood within a much larger cosmic city. Step out farther, and we reach the Virgo cluster, a massive collection of more than 1,000 galaxies bound together by gravity. The Local Group is part of this larger structure, drawn toward Virgo's center at a speed of roughly 600 kilometers per second. But even clusters like Virgo do not stand alone. They gather into still greater formations called superclusters, immense tapestries of galaxies stretching hundreds of millions of light-years across. Our home supercluster is named Laniakea, a Hawaiian word meaning immense heaven. It spans more than 500 million light-years and contains about 100,000 galaxies, connected in a delicate web of filaments and clusters that includes Virgo, Hydra, Centaurus, and others. How do we know this? Astronomers have learned to measure not just where galaxies are, but how they move. Beyond the usual redshift and blueshift that reveal motion toward or away from us, scientists study something more complex: peculiar velocity, the motion of galaxies relative to the overall expansion of the universe. To find it, they need both distance and speed. One key tool is the Tully-Fisher relation, which links how bright a spiral galaxy appears to how fast it spins. Comparing its true and apparent brightness gives its distance. Comparing that distance to its redshift shows whether it moves faster or slower than the general cosmic expansion. That difference reveals how local gravity pulls or pushes it through space. These techniques became the foundation for vast studies known as cosmic flows. The second and third surveys, Cosmic Flows 2 and Cosmic Flows 3, mapped thousands of galaxies using several methods: brightness relations, supernovae, and subtle surface light variations. From these data, astronomers built a three-dimensional map of galaxy motion, showing not just where galaxies sit, but how they stream through the universe. The result was striking. Galaxies were not scattered randomly. They were moving together, flowing toward a hidden region of space behind the thick dust of our own Milky Way. This mysterious source of gravitational pull became known as the Great Attractor. It was first suspected in the 1,970 seconds, when scientists noticed galaxies drifting sideways across the sky at hundreds of kilometers per second, as if pulled by something massive. But when they looked in that direction, the Milky Way's own stars and gas blocked the view. The effect, though, was unmistakable. Something unseen was tugging at everything around it. Later, X-ray and infrared telescopes able to peer through the dust revealed great clusters of galaxies in that region, the largest being the Norma cluster, about 220 million light-years away. But Norma was only part of an even greater structure, the Shapley supercluster, one of the most massive known. Its gravitational strength bends the paths of galaxies across hundreds of millions of light-years. It is this immense formation that draws the local group, the Virgo cluster, and the entire Laniakea supercluster in its direction. Still, our motion through the cosmos is not a simple fall toward a single point. Gravity acts in many directions at once. While the Shapley supercluster pulls us forward, another force shapes our movement differently: the dipole repeller. Unlike the great attractor, it is not made of matter at all. It is a vast cosmic void, an immense region almost empty of galaxies. Though emptiness does not pull, it allows surrounding matter to drift away, creating a balance between attraction and release. Imagine floating in a river. One side is a waterfall drawing you forward the great attractor, while the other side is calm and open, letting you glide away the repeller. You are not pushed, only guided by the flow. In 2017, data from Cosmic Flows 3 confirmed this grand picture. More than 18,000 galaxies showed a dipole pattern motion both toward the great attractor and away from the dipole repeller. It revealed that our galaxy, our cluster, and all the structures around us are part of a much larger current, a slow cosmic stream sweeping through the nearby universe. And beyond even that, when astronomers zoom farther out, the pattern continues, an endless motion, threading through the web of galaxies that fills the cosmos. The great web of the cosmos, the vast structure connecting galaxies and clusters across the universe, is not fixed. It drifts and flows, reshaping itself over time as space continues to expand. Every thread of this immense network is moving towards something greater, something still hidden from our view. As the universe grows, something remarkable is happening. The most distant galaxies are drifting away from us, and they are doing so faster and faster. It is not that these galaxies are racing through space like speeding ships. Rather, space itself is stretching, and as it expands, it carries galaxies along as if they are passengers on a flowing current. This expansion is not slowing down. It is accelerating. Scientists call it the accelerating expansion of the universe. With each passing moment, galaxies move away more quickly, and the farther they are, the faster they seem to flee. One day, many of these galaxies will recede so swiftly that, from our point of view, they will appear to move faster than light. This does not break any law of physics because they are not truly traveling through space at that speed. Instead, it is the space between us that grows. A useful image is that of raisins in bread dough. The raisins stay still within the dough, but as the dough rises, they drift farther apart. This steady expansion shapes the future of the cosmos in ways both awe-inspiring and lonely. Over time, the most distant galaxies will move so far away that even their light will never reach us. They will slip beyond the cosmic horizon, the ultimate limit of what we can ever see. Beyond that boundary, their light cannot outrun the stretching of space, and they will fade forever from our reach. This is not a distant prediction. It is already happening. Light from some galaxies we observe today began its journey billions of years ago, and that light is still being stretched by expanding space. As a galaxy recedes, its light waves lengthen, shifting toward red, a process called redshift. The faster it moves away, the redder its light becomes. Eventually, its light will stretch beyond what our eyes or even our best telescopes can detect. First, it slips into microwave wavelengths, then radio, and finally it vanishes completely into darkness. Billions of years from now, most galaxies will have passed beyond the cosmic horizon. Only a small cluster will remain visible, the galaxies of our local group, held together by gravity. These include the Milky Way, Andromeda, and a few smaller companions. Over time, they will merge into a single massive galaxy. Beyond that, everything else, the billions of other galaxies, stars, and worlds, will fade from view. The far future of the universe will be quiet. Collisions between galaxies will become rare. Star formation will slow, and as eons pass, stars will burn through their fuel and go dark. Without new stars being born, the cosmos will cool and grow still. This distant age is called the heat death of the universe, when energy is spread so thin that nothing new can form, and even light itself becomes faint and cold. Despite this, the laws of physics remain constant for now. The same rules that govern atoms, stars, and galaxies still hold: gravity, thermodynamics, and quantum mechanics. Yet as the universe expands, scientists wonder whether this endless stretching could one day change even those laws. Some physicists question whether the so-called constants of nature are truly constant. The speed of light, for example, is not only the limit for motion, but also the foundation for how information and energy move through space. The gravitational constant sets how strongly objects attract one another, from planets to galaxies. And another key number, the fine structure constant, determines how light interacts with matter. It shapes chemistry, the behavior of atoms, and the possibility of life itself. Even a tiny change in its value could transform the universe. Atoms might not form, stars might not shine, and life might never exist. So far, every measurement shows that these constants remain unchanged. The universe expands, but the rules remain steady. Still, some scientists suspect that in the earliest ages of the cosmos, they might have been slightly different. A few studies hint that the fine structure constant may have varied by an almost immeasurable amount billions of years ago. Though the evidence is uncertain, if true, it would mean the fabric of the universe and its laws have evolved together over time. Driving this expansion is dark energy, a mysterious force that makes up most of the universe but is still poorly understood. It pushes galaxies apart and shapes the large-scale structure of space. Some theories suggest that dark energy itself could be connected to changes in physical constants, or even to the passage of time. If space can stretch, could time itself stretch as well? Could the very rhythm of the universe slow or shift as it grows? These are bold ideas, still beyond what we can test, but they open the door to profound possibilities. Some researchers even imagine that the universe might one day undergo a transformation, a kind of cosmic phase change, like water turning to ice. If that happens, the fundamental laws of physics might rearrange themselves, creating a universe ruled by new principles entirely. This would not happen soon, nor within any timescale humans can comprehend. It may take trillions of years, long after every star has gone dark. Yet, even in imagining such a distant future, there is wonder. The same universe that gave rise to light, stars, and life may still be unfolding, still changing, still writing new chapters in a story too vast for us to finish, but beautiful to glimpse from our small, moving corner of the cosmos. At the start of the 20th century, most scientists believed the universe was timeless and still a grand, eternal stage where stars and galaxies shone in fixed positions that would never change. It was thought that the cosmos had always existed exactly as it appeared, calm and unshakable. But that picture soon began to crumble. A new generation of astronomers started to study the faint light coming from distant galaxies, and among them was a man whose work would reshape our understanding of the universe, Edwin Hubble. Working at Mount Wilson Observatory in California, Hubble used the Hooker telescope, the most powerful telescope of its time, with a mirror 2.5 meters wide. It allowed him to peer deeper into the night sky than anyone before. He examined the faint, hazy patches that earlier astronomers had debated for years. Were these small clusters of stars within our own Milky Way, or were they something much larger? With careful observation, Hubble discovered that many of these patches were entire galaxies of their own, each containing billions of stars and lying far beyond the boundaries of the Milky Way. Overnight, the known universe expanded beyond imagination. But Hubble's discoveries went further. When he studied the light from those distant galaxies, he noticed that much of it was shifted toward the red end of the spectrum. This phenomenon, called redshift, occurs when light waves stretch out, making them appear redder than usual. It works much like the sound of an ambulance siren that changes pitch as it passes high when approaching, lower as it moves away. The same principle, applied to light, reveals motion across space. From this simple shift came a remarkable conclusion. The galaxies Hubble observed were moving away from us. Even more surprising, the farther away a galaxy was, the faster it was retreating. This steady pattern became known as Hubble's law, and it pointed to a profound truth: the universe itself was expanding. Galaxies were not simply drifting through space like boats on a calm sea. Instead, the very fabric of space was stretching, carrying them along like objects resting on the surface of an inflating balloon. If space is expanding now, logic suggests it was once much smaller. Rewinding that process backward through time leads to a single, extraordinary moment when everything, matter, energy, and space itself was compressed into a tiny, hot, dense point. Then, in an instant, it began to expand. This concept became known as the Big Bang Theory, the idea that the universe had a beginning, that it has been changing ever since, and that it is still unfolding even now. When people imagine the expanding universe, they often picture galaxies shooting outward like rockets, racing into empty space. But the truth is gentler and more intricate. Galaxies are not moving through space at high speed. It is space itself that expands, carrying galaxies along with it. The difference may seem small, but it changes how we understand everything. Imagine tiny dots drawn on the surface of a balloon. As you blow air into it, the balloon stretches and the dots move apart, though none of them are actually traveling across the surface. The space between them grows. The universe works in much the same way. This expansion gives rise to one of the universe's strangest features. The farther away a galaxy is, the faster it appears to move away. Some galaxies are so distant that their light will never reach us. No matter how long they shine, the expansion of space increases faster than light can cross it, pushing them beyond our reach. Those distant realms lie outside what scientists call the observable universe, the part from which light has had enough time to reach us since the Big Bang, about 13.8 billion years ago. Despite this grand stretching, the effect is invisible on smaller scales. Gravity binds matter tightly enough that planets do not drift from their stars, and stars stay bound within galaxies. The expansion only reveals itself over immense distances, across millions or billions of light years. Within galaxies and galaxy clusters, gravity wins the contest, holding everything together against the outward pull of space. One of the most surprising aspects of cosmic expansion is that it has no center. There is no single point in space from which everything is flying outward. Instead, the expansion happens everywhere at once. From any galaxy's point of view, all the others seem to be moving away. On our balloon analogy, it doesn't matter which dot you stand on. Every other dot appears to drift from you as the balloon grows. The same is true for galaxies in the universe. This idea took time to accept because it challenges how motion works in daily life. On Earth, movement happens against a fixed background. A car travels down a road, a person walks across solid ground. But in the universe, even the background is moving. The fabric of space itself stretches beneath everything, carrying galaxies and clusters along. It's as though the ground beneath your feet were lengthening with every step, moving you forward without you realizing it. The discovery that the universe is expanding transformed our place in the cosmos. The stars and galaxies are not fixed jewels in a permanent sky. They are part of a living, changing universe that continues to grow, carrying us with it on an endless journey through time and space. The universe has never expanded at a constant pace. Its growth has shifted and changed over billions of years, speeding up and slowing down under the influence of competing forces. Right after the Big Bang, about 13.8 billion years ago, the cosmos went through an instant of staggering growth known as inflation. In less than a fraction of a second, space itself swelled at an incredible rate, smoothing and shaping the early universe. Though it lasted only a heartbeat in cosmic time, inflation set the foundation for everything that would follow. When this burst ended, expansion continued but at a slower rate. A balance formed between two opposing forces, the outward push left over from the Big Bang and the inward pull of gravity. For billions of years, these forces struggled against each other. Expansion worked to separate galaxies, while gravity tried to draw them back together. The result of this tug of war is written across the sky in the grand patterns of galaxy clusters and empty voids that we see today. To measure how fast the universe stretches, scientists rely on a key number called the Hubble constant. This constant describes how quickly galaxies are moving apart for every unit of distance between them. It is measured in kilometers per second per megaparsec, a megaparsec being about 3.26 million light years. In simple terms, the Hubble constant tells us how many kilometers per second a galaxy moves away for each megaparsec of distance. The greater the distance, the faster the recession. Determining this constant with precision is one of the hardest challenges in astronomy. It requires knowing both how far away galaxies are and how fast they are moving. For distance, astronomers often use a type of star called a Cepheid variable. These stars brighten and dim in a steady rhythm, and the timing of their pulses reveals their true brightness. By comparing that intrinsic brightness with how bright the star looks from Earth, astronomers can calculate how far away it is. Once the distance is known, a galaxy's speed can be found by measuring the redshift of its light, the degree to which its light waves have stretched as it moves away. With both pieces of data, the expansion rate can be calculated. In theory, the process seems simple, but in practice, it has sparked one of modern science's biggest puzzles, the Hubble tension. Different methods give slightly different answers for the Hubble constant. The first approach looks at galaxies relatively nearby, using Cepheid variables and certain supernovae as distance markers. This method tends to give a value of about 73 kilometers per second per megaparsec. The second approach looks much farther back in time to study the cosmic microwave background, the faint glow left from the Big Bang when the universe was only 380,000 years old. By analyzing that ancient light with detailed computer models, scientists find a smaller number, closer to 67 kilometers per second per megaparsec. A difference of only a few kilometers per second per megaparsec might sound small, but in cosmology, it is significant. If our models of the universe were complete, both methods should agree. Their disagreement suggests that something in our understanding may be missing. Perhaps dark energy, the mysterious force that drives cosmic expansion, does not behave exactly as expected. Or maybe there were strange forms of matter or energy in the early universe that have since disappeared. Some researchers even wonder if gravity itself changes over vast distances. Einstein's theory of general relativity has passed every test within the solar system and galaxies, but it has never been proven on the scale of the entire cosmos. If gravity weakens or behaves differently across such immense expanses, it might explain the difference between the two results. It is also possible that the problem lies not in physics, but in measurement. Calculating distances to galaxies across billions of light years is extremely difficult, and even small uncertainties in how we interpret Cepheid variables or supernova data can affect the final outcome. Likewise, the computer models used to interpret the cosmic microwave background are incredibly complex, and a small error could shift the derived value of the Hubble constant. As the universe has evolved, the rate of expansion has also changed. In its early days, when matter was dense and tightly packed, gravity's pull was stronger and slowed expansion more effectively. But as galaxies spread apart, gravity's influence weakened. Then, about 4 billion years ago, the universe began to speed up again, pushed outward by dark energy. This acceleration continues today, shaping the universe's large-scale motion and its distant future. To resolve the Hubble tension, astronomers are turning to new generations of instruments. The James Webb Space Telescope, along with other advanced observatories, provides data with unprecedented clarity. By combining its precision with fresh measurements from deep space, scientists hope to uncover the true value of the Hubble constant. That number will not just refine how old or large the universe is, it will help reveal what kind of universe we truly live in and what its long future might hold. The expansion of the universe raises one of the deepest questions in all of science. How does gravity, the force that holds everything together, interact with the stretching of space itself? We know the universe is expanding, meaning that galaxies are drifting farther apart because space is growing. Yet, despite this expansion, galaxies are not being torn apart, and clusters of galaxies remain intact. Gravity acts as the great glue of the cosmos, constantly working to keep matter bound together while space stretches around it. This creates a vast tug-of-war across the universe. Expansion pulls galaxies away from one another, while gravity pulls them back together. The outcome of this balance defines the structure of the cosmos we live in. Gravity, as described by Einstein's general relativity, is not an invisible string but the bending of space and time. Anything with mass, from a grain of sand to a star, warps the fabric of space-time, creating a kind of curved well that draws other objects toward it. The more massive the object, the deeper the curve and the stronger its gravitational pull. Einstein's view of gravity changed how we see the universe. Planets orbit stars because of it, stars group into galaxies because of it, and galaxies gather into clusters because of its reach. Without gravity, space would be only a thin mist of particles with no order or form. There would be no stars to shine, no planets to hold together, no galaxies to fill the night. While gravity keeps the smaller structures of the cosmos tightly bound, expansion dominates over enormous distances. Space does not expand like wind pushing galaxies apart. It stretches itself, carrying galaxies along as if they were raisins inside a rising loaf of bread. On scales of millions or billions of light years, this stretching becomes visible, but within galaxies or small groups of galaxies, gravity wins easily. The stars within a galaxy, held together by their combined mass and the mysterious influence of dark matter, are bound far more strongly than expansion can pull them apart. Our own Milky Way offers a clear example. Its nearest large neighbor, the Andromeda Galaxy, is not receding into the distance. Instead, the two are moving toward each other, drawn together by gravity so powerful that it overwhelms the gentle push of expansion in their region of space. In about 4 billion years, they will meet and merge in a slow, graceful collision, forming a new, larger galaxy. This is why expansion only matters on truly vast scales, the distances between clusters of galaxies rather than within them. Inside galaxy clusters, where hundreds or even thousands of galaxies orbit a shared center, gravity still dominates completely. These clusters are among the largest and most massive structures in existence, held together by their combined gravitational pull. Though the space between clusters stretches, the galaxies within each one remain locked together, circling endlessly like bees around a hive. The question that remains is what will happen in the far future if the universe keeps expanding faster. The cause of this acceleration is something invisible and poorly understood: dark energy. Unlike gravity, which pulls inward, dark energy pushes outward, driving space to grow. If dark energy continues to strengthen, it could one day overpower gravity entirely. In that distant future, some scientists imagine an extreme end called the Big Rip. In this scenario, the accelerating expansion would tear galaxy clusters apart, then galaxies, then stars, planets, and eventually even atoms themselves. The universe would become a silent, empty space, filled only with drifting particles. For now, though, gravity still holds sway across much of the cosmos. It keeps stars turning in their galaxies, galaxies swirling within clusters, and clusters woven into the great web that stretches through space. The endless contest between expansion and gravity continues to shape the universe and everything we see shining in the night sky. As the universe continues to expand, the immense structures within it are changing in quiet but dramatic ways. The great gatherings of matter, galaxy clusters, long filaments, and vast empty voids did not appear all at once. They formed slowly over billions of years as gravity pulled matter together, weaving an enormous cosmic network. Galaxies lie along invisible threads made mostly of dark matter, the unseen substance that outweighs everything we can see, mixed with ordinary matter, the stars, planets, and dust that make up the familiar universe. But gravity is only half the story. While it gathers matter, the expansion of space gently pulls everything apart. This balance between pull and push shapes the universe we see today. Gravity tries to hold galaxies together, while the expansion of space stretches them away from one another. Over time, the growing universe has widened the gaps between galaxies and the great filaments that connect them, slowly reshaping the cosmic web. Imagine a three-dimensional net, its strands made of galaxies. The dense intersections of this web form galaxy clusters, while the thin threads between them stretch across the emptiness. And between these filaments lie enormous voids, regions so vast and empty that entire superclusters could drift through them without touching a single galaxy. Inside clusters, gravity still dominates. Galaxies there move together, their mutual attraction stronger than the gentle stretching of space. But between clusters, the expansion wins. Voids grow larger, filaments thin out, and galaxies that were once neighbors slowly drift apart. Astronomers call this long process cosmic drift. In the early universe, galaxies collided and merged often, sparking bursts of star formation and reshaping their forms. Now, those encounters are rare. The universe grows quieter and lonelier as its structures spread farther apart. Over billions of years, the voids will continue to expand, taking up more and more of the universe. The great filaments that still connect clusters today will stretch until they break, leaving galaxies isolated. Each cluster will become a small island of light, surrounded by immense darkness. For future observers living in such an age, only the galaxies within their own cluster will remain visible. Every other cluster will fade beyond reach, their light redshifted into wavelengths too long for any telescope to detect. This cosmic fading has a profound consequence. The formation of new galaxies will slow and eventually stop. In the past, galaxies were born when gas and dark matter clumped together under gravity. But as the universe expands, matter becomes more thinly spread, and there is less gas left to form stars. The cosmos will continue aging quietly, its bright regions fading one by one, leaving a sparse ocean of isolated galaxies surrounded by growing emptiness. The expansion of space raises another deep question. Could it affect the flow of time itself? Space and time are woven together into a single fabric space-time, as described by Einstein's general relativity. We already know that massive objects like stars and black holes can bend space and slow time. Astronauts orbiting Earth or clocks aboard satellites tick a little differently than those on the ground. But what about the stretching of space across the entire universe? On human scales, the effect is too small to notice. Our clocks tick steadily, the Earth orbits the Sun, and the rhythm of days and seasons goes on unchanged. Yet across millions or billions of light years, expansion begins to influence both light and time. As light travels through expanding space, its waves stretch an effect called redshift. The farther light has to travel, the more it stretches, shifting toward the red end of the spectrum. This stretching also slows our perception of distant events. When we observe a supernova, a massive star exploding billions of light years away, it appears to unfold in slow motion. The light we see is not only redshifted, the event itself seems to last longer because time, as we observe it, has been stretched by the expansion of the universe. This phenomenon is known as cosmic time dilation. Looking into the distant cosmos means not only looking across space, but also looking deep into the past, watching ancient events play out more slowly because the universe has grown during the light's journey to us. Some scientists believe that as expansion continues and accelerates, time itself might behave in stranger ways. In the distant future, as galaxies drift apart and stars burn out, the universe may approach what is called the Big Freeze, or heat death. In that silent era, energy will be evenly spread, no new stars will form, and the universe will grow cold and dark. Without motion or change, time could lose its meaning entirely. If nothing happens, no light, no growth, no decay, then there would be nothing left to mark its passage. Einstein's theory tells us that time is not fixed. It flows differently depending on motion and gravity. Near massive objects like black holes, time slows measurably, a fact confirmed by precise atomic clocks. Could a similar principle apply across the expanding universe? Could the growth of space itself alter the cosmic rhythm of time? We do not yet know. Dark energy, which drives the universe's accelerating expansion, may influence how time unfolds on vast scales, but its nature remains hidden. Some physicists even wonder if time is not a fundamental property at all, but something that emerges from the interactions of space, matter, and energy, a product of motion and change rather than a background it happens against. For now, these questions remain open. The more we study the expanding universe, the more it reminds us that space and time are not static backdrops, but active participants in the cosmic story, shaping, stretching, and carrying everything forward, even the ticking of time itself. If space itself is expanding, what happens to the smallest parts of the universe? Do atoms stretch? Do particles drift apart? The answer lies in the balance between the immense and the infinitesimal. The expansion of the universe mainly affects the vast distances between galaxies. Inside galaxies, and especially within stars, planets, and atoms, the forces that hold matter together are far stronger than the slow pull of cosmic expansion. Within every atom, powerful forces rule. The electromagnetic force keeps electrons bound to the nucleus, while the strong nuclear force holds the nucleus itself together. That strong force is about 100 times stronger than electromagnetism and millions of times stronger than gravity. These are the forces that keep matter intact, the reason the atoms in your body don't stretch, the air doesn't drift apart, and the ground beneath your feet stays solid. Even entire planets and stars feel no effect from the universe's expansion. It is only across the great, nearly empty spaces between galaxies that the stretching of space becomes noticeable. This shows how mighty these tiny forces are. They easily overwhelm the gentle pull of the expanding cosmos. On our scale, the universe feels stable and unmoving. Yet scientists still wonder whether, deep down, there could be subtle links between the vastness of space and the quantum world, the realm of particles smaller than atoms. Quantum physics tells us that even empty space is not truly empty. It constantly flickers with energy, producing tiny, short-lived particles that appear and vanish faster than we can imagine. These quantum fluctuations happen everywhere, all the time, though they are far too small to see. Some physicists believe that these fleeting events played a role in shaping the entire universe. Right after the Big Bang, about 13.8 billion years ago, the universe went through a period of astonishing growth known as cosmic inflation. In less than a trillionth of a second, space expanded at a rate faster than light, something not forbidden by physics because it was space itself that was stretching. In that moment, the universe grew from smaller than a single atom to something vast enough to contain the seeds of galaxies. Here is the remarkable part. Those tiny quantum ripples that existed before inflation were stretched and magnified along with space. They became faint patterns in the fabric of the cosmos, slight uneven spots in energy and density that later grew into galaxies, stars, and planets. The entire structure of the universe may have started from those microscopic fluctuations, linking the quantum world to the largest scales we can imagine. Some scientists also think that dark energy, the mysterious force driving the universe's accelerating expansion, might have its roots in the same quantum realm. If that is true, then the slow growth of space today could be connected to the restless energy of the quantum vacuum, a bridge between the smallest and largest scales of nature. The story of how the universe began is far from gentle. Immediately after the Big Bang, space underwent a wild, almost unimaginable transformation. During inflation, the cosmos expanded enormously in less than a blink, less than a trillionth of a second. What had been smaller than an atom suddenly stretched to a size that could encompass galaxies. That instant of inflation changed everything. Before it, the young universe was chaotic and blazing hot, filled with a thick, glowing mixture of particles and energy. Then, in a flash, space itself ballooned outward, smoothing the uneven chaos. Most of the early lumps and irregularities vanished, leaving behind a surprisingly even, balanced cosmos. Though not perfectly smooth, tiny ripples in density survived, barely noticeable at first. But over billions of years, they became galaxies, stars, and eventually planets. Without that sudden burst of expansion, the universe might have remained too rough and clumpy for galaxies or life to ever form. Inflation made the cosmos vast, mostly smooth, but gently varied. Those small imperfections, born from quantum whispers at the dawn of time, became everything we see today. The galaxies in the night sky, the stars that light them, and the living beings who gaze back, wondering how it all began. The rapid burst of inflation in the early universe eventually gave way to a slower, steadier expansion that has continued ever since, shaping the vast cosmos we see today. For much of the 20th century, scientists assumed this expansion would gradually slow down. It seemed reasonable gravity, pulling on every bit of matter and energy, should eventually resist the outward motion of space itself. But in the late 1990 seconds, that expectation was shattered. Two teams of astronomers studying a special kind of exploding star known as a Type Ia supernova made a discovery that changed everything. These supernovae shine with a predictable brightness, making them reliable tools for measuring cosmic distances. By observing how bright or dim they appear, astronomers can tell how far away they are, and from the redshift of their light, how fast they're moving. When researchers compared supernovae in distant galaxies with those closer to us, the results were astonishing. The distant ones appeared dimmer than they should have been if the universe's expansion was slowing. The only explanation was that the expansion was speeding up. That realization forced science to confront a new mystery. What was pushing the universe apart? The answer came in the form of an idea now called dark energy, a strange, invisible force that seems to fill all of space, working against gravity and driving galaxies away from one another. Today, astronomers estimate that dark energy makes up roughly 70% of the total energy of the universe. Yet what it actually is remains one of the deepest puzzles in physics. Unlike ordinary matter, which clumps together into stars and planets, or even dark matter, which gathers around galaxies, dark energy does not cluster. It appears smooth and uniform, filling space evenly everywhere we look. Even as space expands, dark energy does not thin out. It seems to generate more of itself, filling the new space as it appears. It behaves almost as though it is woven into the very fabric of the cosmos. The more the universe grows, the more dark energy there is, which in turn drives even faster expansion, a self-feeding cycle like a snowball rolling down a hill. One possible explanation comes from an idea first introduced by Albert Einstein more than a century ago. When he developed his theory of general relativity, most scientists thought the universe was static and unchanging. To make his equations fit that belief, Einstein added a mathematical term called the cosmological constant, a force that would counteract gravity and keep the universe in balance. Later, when Edwin Hubble discovered that the universe was actually expanding, Einstein discarded the constant, calling it his biggest mistake. Yet the discovery of dark energy brought that old idea back to life. Many scientists now think the cosmological constant may be real after all, a built-in energy of empty space itself. If dark energy continues to dominate, what will become of the universe? One possible outcome is the Big Freeze. In this distant future, galaxies will drift farther apart until their light can no longer reach one another. Stars will burn out one by one, leaving a cold, dark cosmos filled only with fading remnants. Another, more extreme scenario is called the Big Rip. If dark energy grows stronger over time, it could eventually tear apart galaxies, stars, and even the atoms that make up matter. Space itself would stretch everything to pieces, ending the universe in silence. Right now, we know only that dark energy rules the large-scale behavior of the cosmos. It accounts for about 68% of the total content of the universe. Dark matter contributes about 26%, shaping galaxies through its gravity. The ordinary matter that makes up all stars, planets, and life, everything we can actually see, represents only about 5%. The rest is filled with faint traces of radiation and ghost-like particles, such as neutrinos. Even though dark energy has an almost unimaginably low density, just a few atoms worth of mass spread across a space the size of a house, it dominates because it exists everywhere. It fills every corner of space, no matter how empty it seems. The first clear evidence for it came from those same supernova studies of the 1,990 seconds, which revealed that distant galaxies were receding faster than expected. That discovery changed our understanding of cosmic destiny forever. Scientists are still exploring what dark energy might be. The leading explanation remains Einstein's cosmological constant, the idea that the energy of space itself never changes and has been present since the beginning. But there are other possibilities. Some theories suggest that dark energy comes from a scalar field, a kind of energy that varies across space and time. These versions, often called quintessence, imagine dark energy as something dynamic, slowly evolving, instead of staying fixed. Others propose that dark energy interacts with gravity in ways we do not yet understand, subtly altering how space expands on the largest scales. It is even possible that the connection between dark energy and gravity is deeper than we realize. In the early 20th century, Einstein invented the cosmological constant to balance the universe. Nearly a century later, scientists discovered that the cosmos truly does contain a mysterious repelling force, one that pushes everything apart. What Einstein once called his greatest mistake may, in the end, have been one of his most profound insights. In 1980, physicists Alan Guth and Alexei Starobinsky proposed a bold idea that would reshape our understanding of the early universe. They called it cosmic inflation, a theory suggesting that just after the Big Bang, the universe experienced a moment of extraordinary, almost explosive growth. In less than a trillionth of a second, space expanded faster than the speed of light, transforming the infant cosmos from something unimaginably tiny into a vast, smooth, and uniform expanse. This brief but powerful event laid the groundwork for everything that followed, explaining why galaxies are distributed the way we see them today. Inflation and dark energy share a curious resemblance. Both cause space to expand rapidly, but the energy that drove inflation was far more intense than the dark energy now stretching the cosmos. Whether these two phenomena are connected or entirely separate remains one of the great open questions in cosmology. By the 1,980 seconds, researchers had built models of the universe based on what they called cold dark matter, a slow-moving form of matter that doesn't emit light. These models did a good job explaining how galaxies formed, but some predictions didn't quite match observations. For example, they suggested a slower cosmic expansion rate, the Hubble constant, than astronomers were actually measuring. Then came the data that changed everything. In 1992, NASA's COBE spacecraft detected faint ripples in the cosmic microwave background, the ancient glow left over from the Big Bang. These tiny temperature variations showed how the first seeds of galaxies were distributed, giving scientists a new blueprint for understanding cosmic structure. The picture grew even clearer in 1998, when astronomers studying distant supernovae found undeniable evidence that the universe's expansion was not slowing down, it was accelerating. That discovery marked the first direct proof that dark energy was real. In the years that followed, new experiments reinforced this strange revelation. Balloon-based missions like Boomerang and Maxima in the early 2000s examined the cosmic microwave background in greater detail, revealing that the universe is flat on large scales. In other words, its overall geometry perfectly balances between open and closed. But there was a problem. The amount of matter, ordinary and dark, accounted for only about 30% of what was needed to achieve that flatness. The missing piece was identified as dark energy. More evidence arrived in 2001 from the 2-degree field galaxy redshift survey, which mapped how galaxies are distributed across space. The data made it clear that some unseen force was shaping the large-scale structure of the cosmos. Then, from 2003 to 2010, NASA's WMAP satellite refined these measurements, confirming the now famous Lambda Cold Dark Matter model, LCDM, as the best overall description of the universe. The lambda refers to Einstein's cosmological constant, representing dark energy, while cold dark matter accounts for the invisible matter that sculpts galaxies. The phrase dark energy itself was coined in 1998 by physicist Michael Turner, echoing an earlier term, dark matter, introduced in the 1930 seconds by Fritz Zwicky. Despite decades of progress, dark energy remains one of the most profound mysteries in science. Some physicists think it's a property of space itself. Others suspect it's rooted in quantum mechanics, the laws that govern subatomic particles. To study it, scientists rely on extraordinarily precise measurements of the universe's expansion. In general relativity, this expansion is described by something called the cosmological equation of state, which relates pressure, density, and energy to the curvature of space. Determining the equation of state for dark energy, essentially how it behaves, is one of the hardest challenges in modern physics. The LCDM model, built from the equations of Einstein and Friedman, has become the gold standard of cosmology because it matches observations so well. Since 2013, it has been tested with exquisite precision using data from the Planck satellite and the Supernova Legacy Survey. These studies suggest that dark energy behaves almost exactly as Einstein's cosmological constant predicts, with remarkable accuracy within about 10%. Observations from the Hubble Space Telescope's Higher Z team have shown that dark energy has been influencing the universe for at least 9 billion years, long before the acceleration began in earnest. Yet, despite all this progress, its true nature remains elusive. It appears smooth, uniform, and astonishingly weak in density, roughly 10 to the power of -27 kilograms per cubic meter. That's less mass than a single proton in a volume the size of a human body. And yet, this faint, invisible energy makes up nearly 70% of the total content of the cosmos. One popular explanation is that dark energy arises from vacuum energy, the subtle fluctuations of empty space predicted by quantum theory. According to Heisenberg's uncertainty principle, Even the void is alive with virtual particles flickering in and out of existence. These microscopic changes, when summed across the entire universe, should produce a tiny but measurable pressure, what Einstein called the cosmological constant. But there's a staggering mismatch between theory and observation. When physicists calculate how much vacuum energy quantum mechanics should create, the number comes out more than 100 orders of magnitude larger than what we actually observe. It is perhaps the single greatest discrepancy in all of science, a gap between the quantum world and the cosmic one that no theory yet bridges. Whatever its origin, dark energy must exert a negative pressure, meaning it pushes rather than pulls. In Einstein's equations, both mass and pressure affect gravity, captured together in the stress-energy tensor. Positive pressure, like that inside a star, adds to gravity's pull. Negative pressure does the opposite. It acts as a kind of gravitational repulsion, driving galaxies apart and accelerating the expansion of space itself. As the universe grows, its ingredients evolve differently. Matter, everything with mass, from stars to dust, dilutes as space expands, its density dropping by the cube of the universe's growth factor. Radiation, such as light and heat, thins out even faster because its wavelengths stretch in addition to its spreading. But dark energy behaves unlike either of these. Its density doesn't change. No matter how large the universe becomes, dark energy remains constant, filling all of space equally. And that is why, as galaxies drift farther apart and stars burn out, dark energy will continue to dominate an invisible tide, pushing the universe toward an ever colder, quieter, and more mysterious future. Scientists now have many clues that dark energy is real, even though it has never been directly detected. One of the strongest pieces of evidence comes from how light travels through space. When astronomers look at the light from faraway galaxies and supernovae, they see that its wavelengths have stretched more than expected. This stretching, called redshift, shows that the universe has been expanding faster in recent times than it did in the past. Something, likely dark energy, must be causing this acceleration. Another clue comes from the overall shape of the universe. Measurements show that space is flat, meaning it doesn't curve inward or outward on a large scale. For that to be true, the total amount of energy in the universe must reach a precise balance. Yet when scientists add up all the visible matter and dark matter, they come up short. The missing energy that keeps the universe flat must come from something else, something like dark energy. Patterns in how galaxies are spread across the cosmos also point to it. The large-scale structure of the universe, the web of galaxy clusters, filaments, and empty voids, only makes sense if some unseen force has been influencing how space itself grows. The turning point came in 1998, when the High Z supernova search team studied a special kind of stellar explosion called a Type Ia supernova. These explosions are so bright and uniform that they can be used as cosmic yardsticks. Astronomers expected to see that distant supernovae were slowing down as gravity pulled everything together. Instead, they found the opposite. The universe was speeding up. Just a year later, the Supernova Cosmology Project reached the same conclusion. Their discovery completely changed our understanding of the cosmos and earned the 2011 Nobel Prize in Physics. Since then, every new observation has reinforced that result. Studies of the cosmic microwave background, the faint glow left from the Big Bang, showed temperature patterns that matched an accelerating universe. Astronomers have also used gravitational lensing, the bending of light by massive objects, to confirm that galaxies and clusters are moving apart faster than gravity alone could explain. Type Ia supernovae remain one of the best tools for tracking this expansion, Because they all explode with nearly the same brightness, scientists can compare how bright they appear from Earth to determine their distances. By pairing those distances with redshift measurements, they can map how fast the universe has been growing over time. Recent data suggests that about 71% of the universe is dark energy, while the remaining 29% is split between dark matter and normal matter. The leading cosmological models, those describing how galaxies and stars form and evolve, indicate that matter accounts for only about 1/3 of the energy needed for the universe to stay flat. The rest must come from dark energy. More evidence arrived in 2011 from the Wigglesy Galaxy Survey, which measured the positions of more than 200,000 galaxies. By using new techniques to estimate their distances, researchers confirmed again that the universe's expansion is accelerating. Observations from NASA's Wilkinson Microwave Anisotropy Probe showed that dark energy makes up about 73% of the cosmos. Later, data from the Planck satellite refined this number to around 68%, with dark matter making up about 27% and ordinary matter less than 5%. Even subtle effects in the cosmic microwave background support the existence of dark energy. When light from that ancient radiation passes through regions with strong gravity, such as galaxy clusters or vast voids, it gains or loses energy. This creates tiny temperature shifts known as the integrated Sachs-Wolf effect, one more piece of evidence pointing to an accelerating universe. Astronomers are also finding new ways to measure expansion over cosmic history. One method uses certain types of galaxies as cosmic clocks. By studying their ages and how their light is redshifted, researchers can calculate how quickly the universe was expanding at different points in time. Despite all this evidence, dark energy remains one of the deepest mysteries in physics. Scientists agree it drives the universe's faster expansion, but they still don't know what it actually is. Some researchers are testing Einstein's theory of gravity to see if small adjustments might explain the data. Others are searching for the physical nature of dark energy itself. The simplest idea is that dark energy is a built-in property of space, a form of vacuum energy. Even what we call empty space isn't truly empty. Quantum physics says it's filled with fleeting particles that appear and vanish endlessly. This energy, sometimes represented by the Greek letter L, lambda, forms the basis of the lambda cold dark matter model, the leading theory of cosmology today. But there's a serious problem. When physicists calculate how much vacuum energy should exist using quantum theory, the result is staggering, about 10 to the power of 120 times greater than what we observe. If that number were right, the universe would have expanded so rapidly that no galaxies, stars, or planets could have ever formed. Something must be canceling out almost all of that energy, but not quite all of it. That tiny leftover amount might be what we see as dark energy. Why the numbers don't match is still unknown. It may be that our theories of quantum physics or gravity are incomplete, or that an entirely new kind of physics is waiting to be discovered. For now, dark energy stands as one of the universe's most enduring riddles, an invisible presence shaping the fate of everything, even as its true nature remains hidden. While many scientists picture dark energy as a steady, unchanging force woven into the fabric of space, others imagine something far more dynamic, a living field that evolves with time. This idea is called quintessence. Instead of being uniform everywhere, like Einstein's cosmological constant, quintessence behaves more like an invisible mist that changes strength from place to place, subtly altering how the universe expands. It is thought to be extremely light and diffuse, which is why, unlike ordinary matter, it doesn't clump into stars or galaxies. Some versions of this idea suggest that cosmic expansion might actually be happening a little slower than standard models predict, though the evidence so far is not decisive. The deeper mystery, though, is why now? Why did dark energy begin to dominate only in the recent cosmic past, roughly 5 billion years ago, after billions of years when gravity was in charge? If dark energy had taken over earlier, galaxies might never have formed, and life would have had no chance to appear. Some scientists see this as pure coincidence. Others interpret it through the anthropic principle, the controversial idea that the universe must be the way it is because we exist within it to notice. Certain quintessence models even have built-in mechanisms called trackers that could naturally explain this timing. In these scenarios, dark energy's strength evolves in step with the universe's changing balance of radiation and matter, only becoming dominant once the cosmos had aged enough for structures like galaxies and stars to form. Then there are the wilder possibilities. One extreme version, known as phantom energy, imagines a form of dark energy that grows stronger over time instead of remaining steady. In this version of the future, the expansion would eventually overwhelm every force that holds matter together. First, galaxies would drift apart, then stars and planets would be torn from their orbits, and finally even atoms would be pulled to pieces. The universe would end in a catastrophic finale known as the Big Rip, a moment when space itself tears apart. Another idea, K-essence, proposes that dark energy might be made of exotic energy fields that behave in entirely new ways. Some K-essence theories even predict strange effects like negative kinetic energy, which could produce bizarre and unpredictable outcomes for the evolution of the universe. Meanwhile, astronomers are facing another puzzle closer to home, the Hubble tension. Measurements of how fast the universe is expanding today don't perfectly match predictions from early universe data. Some researchers suspect that quintessence, or other time-varying forms of dark energy, could help explain this mismatch. Others think the tension might hint at deeper flaws in our understanding of physics itself. Dark energy's mystery is inseparable from Einstein's general relativity, the theory that connects space, time, and gravity. Some scientists have suggested that we might not need dark energy at all if relativity itself changes under certain conditions. Modified gravity models, such as FR gravity or brane world theories, try to explain cosmic acceleration without invoking dark energy. But many of these ideas were dealt a serious blow in 2017 when the detection of gravitational waves from a neutron star merger, known as GW170817, showed that gravity waves travel at the same speed as light. That single observation ruled out a large number of these alternative theories, reinforcing the view that dark energy, in some form, must be real. Astrophysicist Ethan Siegel puts it bluntly: while alternative explanations make headlines, none match the precision of current observations as well as dark energy does. The data tell a consistent story. About 5 billion years ago, the expansion of the universe began to speed up. Before that, gravity, mostly from dark matter, was slowing everything down. As the universe expanded, dark matter thinned out, while dark energy remained nearly constant. Eventually, it took over, and the cosmic expansion entered a new, accelerating era. Each time the universe doubles in size, the amount of matter in any given volume drops by half, but dark energy stays the same, filling all of space evenly. If it truly is constant, the universe will keep expanding forever. Distant galaxies will accelerate away from us faster and faster, eventually crossing a boundary called the cosmological event horizon. beyond which their light will never reach us. That horizon lies about 16 billion light years away today. Anything beyond it is already lost to eternity. As galaxies approach that edge, their light will stretch into longer wavelengths, first infrared, then radio, and finally into signals too faint to detect. To future observers, they will seem to fade from existence, leaving only our local group, the Milky Way, Andromeda, and a handful of smaller galaxies floating alone in an endless dark sea. Still, this lonely fate is not the only possibility. If dark energy grows stronger over time, the Big Rip may await a final disintegration of all structure. But if dark energy weakens or reverses, the expansion could slow, stop, and then reverse. In that case, gravity might pull everything back together into a fiery collapse known as the Big Crunch, perhaps followed by another explosion, another Big Bang, and the birth of a new universe. Between eternal expansion, a violent rip, or a cyclical rebirth, the truth remains hidden in the dark. What we do know is that the universe is not static. It breathes, it changes, and it evolves. And somewhere in that grand motion lies the secret of dark energy, the quiet architect of cosmic destiny. Some scientists imagine that dark energy might not be constant at all. Instead, it could rise and fall in cycles, driving the universe through endless phases of expansion and collapse, with each Big Bang followed by a Big Crunch. Alongside this mysterious energy is another unseen ingredient shaping the cosmos: dark matter. Unlike the familiar matter that forms stars, planets, and people, dark matter doesn't shine or absorb light. It doesn't interact with radiation at all. We know it exists only because of how its gravity tugs on everything else. Astronomers see its fingerprints everywhere, in how galaxies spin, in the way light bends as it passes massive objects, a phenomenon called gravitational lensing, and in the large-scale patterns that fill the universe. Even the faint afterglow of the Big Bang carries its subtle influence. Together, these clues form a picture where dark matter acts as the hidden scaffolding of the cosmos, guiding how galaxies and clusters take shape. In the most accepted model of the universe, the lambda-cold dark matter model, or LCDM, roughly 5% of the cosmos is ordinary matter. About 27% is dark matter. The remaining 68% is dark energy. That means nearly 95% of everything that exists is invisible to us. Of that, dark matter alone makes up about 85% of all matter. Yet, after decades of searching, its true identity is still unknown. Dark matter interacts with ordinary matter only through gravity, which makes it incredibly hard to detect directly. One idea is that it's made of unknown particles called WIMPs, weakly interacting, massive particles that pass through normal matter without leaving a trace. Another possibility is that it's made of particles called axions, extremely light and elusive. Some researchers even wonder if dark matter could come from primordial black holes, tiny ancient black holes formed just after the Big Bang. Scientists describe dark matter as cold, warm, or hot, depending on how fast its particles move. The leading theory is that it's cold, meaning its particles travel slowly. This slow motion allows dark matter to gather into clumps over time, creating the gravitational framework where galaxies can form and grow. But not everyone is convinced. A small number of scientists think the strange motions of galaxies might not need dark matter at all, that perhaps our understanding of gravity itself needs to be revised. Ideas such as modified Newtonian dynamics and other theories of gravity have been proposed, but none can explain all the evidence as well as dark matter can. Even if gravity needs a small correction, dark matter still seems essential to the universe's structure. The story of dark matter stretches back more than a century. In the late 1800s, the Scottish physicist Lord Kelvin began thinking about how stars move through our galaxy. He noticed that their speeds didn't quite make sense if the Milky Way contained only the matter we could see. He wondered if unseen material might be affecting their motion, an early hint of invisible mass. A few decades later, in 1906, French scientist Henri Poincaré used the term matière obscure, or dark matter, while discussing Kelvin's ideas. He proposed that hidden mass might exist throughout space, though he believed it was less abundant than the visible kind. His concept wasn't fully correct, but it helped bring the idea of invisible matter into scientific discussion. By the 1922, astronomers were gathering more clues. Dutch astronomer Jacobus Kapteyn suggested that unseen mass could explain the motions of stars in the Milky Way. Swedish astronomer Knut Lundmark expanded on the idea, realizing that the total mass of the universe must far exceed what telescopes could observe. These early hints paved the way for deeper discoveries. Then, in 1932, Jan Oort, another Dutch astronomer, studied how stars near our galaxy's edge were moving. He found that the Milky Way seemed to contain much more mass than was visible. Although later studies showed his calculations were not entirely correct, his work strengthened the case for something hidden shaping galactic motion. Just a year later came a major breakthrough. Swiss astrophysicist Fritz Zwicky, working at Caltech, analyzed a large collection of galaxies known as the Coma Cluster. He discovered that the galaxies were moving far faster than expected if only the visible matter were providing gravity. Zwicky proposed that an enormous amount of unseen material, dunkel, materia, or dark matter, must be holding the cluster together. He estimated that the cluster had hundreds of times more mass than could be observed directly. Although his numbers were not perfect, his insight was revolutionary. Zwicky was the first to suggest that most of the universe's mass is invisible, exerting its pull through gravity alone. He believed dark matter was made of ordinary material that simply didn't emit light, a view later replaced by the modern idea that it's something entirely different, made of unknown particles. Still, his bold proposal marked the true beginning of our understanding of the hidden side of the universe, an unseen structure that continues to shape the stars, galaxies, and the fate of the cosmos itself. In the decades that followed, evidence for dark matter grew stronger. In 1939, astronomer H.W. Babcock measured how the Andromeda galaxy rotated and found that stars far from its center were moving much faster than expected. He first thought the strange pattern might come from errors in observing light, but his results hinted at something unseen, a hidden mass shaping the galaxy's motion. A year later, Jan Oort found that another galaxy, NGC 3115, was surrounded by a vast, invisible halo of matter. These early findings suggested that galaxies contained far more material than what telescopes could reveal. Still, the idea of dark matter did not fully take hold until the 1972, when a series of independent studies brought the mystery back into focus. In 1974, two research teams, one at Princeton, led by Jeremiah Ostraker, Jim Peebles, and Amos Yahiel, and another in Estonia, led by John Einasto and colleagues, came to the same startling conclusion. Galaxies must be surrounded by enormous halos of invisible matter. Around the same time, astronomer Vera Rubin, working with Kent Ford, used a new kind of spectrograph to measure how fast spiral galaxies spun. Instead of slowing at their edges, as predicted by classical physics, they kept rotating at almost the same speed. Radio astronomers studying the 21-centimeter hydrogen line confirm the same thing. Hydrogen gas extends much farther than visible stars, so these radio measurements trace the galaxy's outer regions. The results were astonishing. The spinning curves of galaxies stayed flat even far beyond the visible edge. Observations of the Andromeda Galaxy with the Green Bank and Jodrell Bank radio telescopes made this especially clear. By 1975, Roberts and Whitehurst extended these measurements out to 30 kiloparsecs, proving that the galaxy's outer regions were packed with unseen mass. This behavior broke the expectations set by Kepler's laws, which describe how planets slow down as they orbit farther from the sunday. In galaxies, stars far from the center did not slow down. They kept moving just as fast. The only explanation was that massive halos of invisible material surrounded each galaxy. Other radio studies in the early 1970 seconds, such as those by Rogstad and Shostak, confirmed that this flat rotation pattern was common. By the end of the decade, most astronomers accepted that dark matter halos were real. Through the 1980 seconds and 1990 seconds, further evidence piled up. Large studies of hundreds of spiral galaxies, such as one by Persic, Solucci, and Stell in 1996, showed that the same pattern appeared everywhere. Observations of gravitational lensing, where light bends around massive clusters, and of hot gas detected in X-rays also pointed to enormous amounts of hidden mass. Subtle temperature variations in the cosmic microwave background, the faint radiation left from the Big Bang, provided yet another line of proof. In the current cosmological model LCDM, or lambda cold dark matter, roughly 5% of the universe is ordinary matter, 27% is dark matter, and the remaining 68% is dark energy. That means almost everything in the cosmos is invisible. Dark matter behaves like regular matter in that it has mass and responds to gravity, but it does not emit or absorb light. It interacts only through gravity, making it almost impossible to detect directly. Scientists think it could be made of undiscovered particles, such as WIMPs, weakly interacting massive particles, or axions, or perhaps of tiny ancient black holes that formed in the earliest moments after the Big Bang. The mystery is also visible in how galaxies move within clusters. Astronomers can measure a cluster's mass in 3 independent ways: from the speed of its galaxies, from the X-rays given off by its hot gas, and from how its gravity bends light, an effect predicted by Einstein and known as gravitational lensing. All 3 methods agree. Each cluster contains roughly 5 times more dark matter than visible matter. Gravitational lensing itself has become one of the strongest proofs of dark matter. When a massive object, such as a galaxy cluster, lies between us and a distant source, its gravity bends the light, distorting or magnifying the background object. In extreme cases, it produces bright arcs and multiple images, as seen in clusters like Abell 1689. Weaker forms of lensing cause only slight distortions, but when astronomers map these effects across the sky, the patterns of invisible mass match what dark matter models predict. Dark matter also shaped the early universe in profound ways. Ordinary matter, being charged, interacted with radiation and couldn't clump together easily in the hot, dense beginning. Dark matter, unaffected by light, could start gathering much earlier, creating gravitational wells that later drew in normal matter. Without it, the universe wouldn't have had time to form galaxies, stars, and planets. We can see the imprint of this process in the cosmic microwave background, the faint glow from 13.8 billion years ago. Tiny temperature differences in this radiation, only 1 part in 100,000, reveal how matter was distributed when the universe was young. Satellites like COB in 1992, Boomerang in 2000, WMAP, and Planck later on measured these fluctuations with increasing precision. The resulting data fit perfectly with the LCDM model, confirming that dark matter played a central role in building the universe's large-scale structure. One of the most striking visual proofs comes from the Bullet Cluster, the result of 2 massive galaxy clusters colliding. When they crashed, the hot gas ordinary matter slowed down and glowed brightly in X-rays. But gravitational lensing revealed that most of the mass had passed through unaffected, separating from the visible gas. This invisible component is dark matter, moving freely through the collision. The Bullet Cluster provides direct, visual evidence that most of the universe's mass is not made of stars or gas, but of something unseen. Today, dark matter remains one of science's greatest mysteries. We can map its influence across billions of light years, yet we still do not know what it is made of. It holds galaxies together, bends the path of light, and sculpts the cosmic web itself, an invisible architecture supporting everything we see in the night sky. Astronomers have many ways to study the hidden universe. One of their most powerful tools is the Type Ia supernova, a kind of exploding star that shines with predictable brightness. Because every Type Ia supernova reaches roughly the same peak luminosity, scientists can use them as standard candles. By comparing how bright they appear to how bright they truly are, they can calculate precise distances across billions of light years. Measurements from these supernovae revealed that the universe is not just expanding, it's expanding faster and faster. A discovery that pointed directly to the existence of dark energy. Another important clue comes from something called baryon acoustic oscillations, or BAO. In the early universe, sound waves rippled through the hot, dense mixture of light and matter. When the universe cooled enough for atoms to form, these waves froze into place, leaving faint imprints in how galaxies are spread out today. The effect is subtle, a small preference for galaxies to be separated by about 147 million light years, but measurable. Surveys such as the Sloan Digital Sky Survey and the 2-degree Field Galaxy Redshift Survey confirmed these patterns in the 2000s. By combining BAO results with data from the cosmic microwave background, scientists refined key cosmic measurements, including the universe's expansion rate and total matter content. Together, these findings support the lambda-cold dark matter model, LCDM, now the cornerstone of modern cosmology. To map galaxies in 3 dimensions, astronomers study their redshift, the stretching of light as it travels through expanding space. However, redshift also carries another signal, the galaxy's own motion, called peculiar velocity. Galaxies in dense regions like superclusters move differently from those in the emptier voids. Superclusters slow the expansion around them as gravity pulls matter inward, while voids expand faster than average. This difference slightly distorts how clusters and voids appear in redshift maps. Clusters seem flattened and voids stretched. These distortions, predicted in the 1,980 seconds and confirmed by later surveys, provide yet another test of the LCDM model. Astronomers also study a delicate feature known as the Lyman alpha forest thin absorption lines in the light from distant quasars. These lines come from clouds of hydrogen gas lying between us and those quasars, tracing the distribution of matter through space and time. Observations of this forest fit remarkably well with models that include both dark matter and dark energy. Dark matter itself comes in different theoretical varieties. Scientists describe it as cold, warm, or hot, depending on how quickly its particles moved in the early universe. The key idea is called the free streaming length, how far those particles could travel before cosmic expansion slowed them down. Cold, dark matter particles moved slowly and stayed close to where they formed, allowing small structures like galaxies to take shape early. Warm, dark matter would have smoothed out small structures, and hot, dark matter, moving nearly at the speed of light, would have erased them entirely. Observations show that galaxies appeared early and later gathered into clusters, which fits best with the cold dark matter model. This also rules out fast-moving particles like neutrinos as the main component of dark matter. At first, some scientists thought dark matter might simply be made of ordinary but hard-to-see objects, planets, faint stars, or black holes. These are called MASHOs, short for massive compact halo objects. While MACOs certainly exist, detailed studies of how light bends around galaxies through gravitational lensing show they cannot account for most of the missing mass. The Big Bang Theory also limits how much normal, or baryonic, matter could exist, because too much would have changed the amounts of helium and lithium we see today. Measurements of the CMB confirm that baryonic matter makes up only about 5% of the universe, while the total matter content is closer to 30%. The rest must be something new, non-baryonic dark matter. Many candidates have been proposed for this unseen material. The most studied are WIMPs, weakly interacting massive particles. These hypothetical particles would have formed naturally in the early universe and survived until today, interacting only through gravity and the weak nuclear force. The WIMP miracle is that such particles, with masses around 100 billion electron volts, would produce just the right amount of dark matter we observe. This neatly matches ideas from supersymmetry, a theory that extends the standard model of particle physics. For decades, scientists have searched for WIMPs by looking for their collisions in detectors deep underground, by studying gamma rays or neutrinos from their possible annihilations in space, and by trying to create them in particle accelerators like the Large Hadron Collider. So far, none have been confirmed. Because WIMPs remain elusive, attention has shifted to another elegant idea: axions. These ultralight particles were first proposed in the late 1970 seconds by Frank Wilczek and Steven Weinberg to solve a problem in quantum chromodynamics, the theory of how quarks and gluons behave. Axions could have been created in vast numbers just after the Big Bang, forming a cold, invisible background throughout the cosmos. Their extremely small mass and weak interactions make them almost impossible to detect, but new experiments using strong magnetic fields and sensitive radio detectors are now searching for their signal. If axions exist, they could explain several puzzles that the standard LCDM model struggles with, such as the exact shapes of small galaxies and the smoothness of dark matter on tiny scales. They may even bridge the worlds of particle physics and cosmology, connecting the universe's smallest building blocks with its grandest structures. Dark matter remains one of the most enduring mysteries in science. It holds galaxies together, shapes the cosmic web, and silently influences the expansion of space itself. Whether it is made of heavy WIMPs, light axions, or something entirely unknown, It continues to remind us that most of the universe, the part that truly defines its structure and fate, lies hidden beyond the reach of light. Primordial black holes offer one of the most intriguing possibilities for dark matter. Unlike the black holes born from collapsing stars, these may have formed in the first seconds after the Big Bang, when dense regions of matter collapsed during inflation. The idea, first proposed in the late 1960 seconds by Zeldovich Novikov and later Stephen Hawking, suggests that some of these black holes could have masses ranging from tiny atomic scales to much larger than stars. The discovery of gravitational waves in 2015 revived interest, as some of the merging black holes LIGO detected were heavier than expected. Yet searches for microlensing events and other signals have not found clear evidence. Voyager 1 measurements and observations of the Andromeda Galaxy also suggest that primordial black holes are too rare to make up most dark matter, though a few mass ranges remain open. If dark matter is instead made of particles, why doesn't it form stars or planets? The reason is that dark matter cannot cool down. Ordinary matter radiates away energy, allowing it to collapse into dense objects. Dark matter barely interacts, so it cannot lose energy. Particles that fall together heat up and drift apart instead. Nor does it experience the electromagnetic or nuclear forces that help ordinary matter form atoms and stars. It interacts only through gravity, so it remains diffuse, shaping galaxies but never lighting them. Scientists hunt for these particles in two main ways. Direct detection experiments look for rare collisions between dark matter and atomic nuclei deep underground. Instruments filled with supercold crystals or pure liquid xenon wait for the faintest flashes of light or heat. Projects like Xenon, Lux, CREST, and Super CDMS push these limits to ever greater sensitivity. Indirect detection looks for the debris from dark matter particles destroying or decaying into gamma rays, positrons, or neutrinos, especially from dense regions such as the Milky Way's center or the Sun's core. So far, no signal has been confirmed, but each new experiment tightens the bounds on what dark matter could be. A third approach tries to create dark matter in laboratories. The Large Hadron Collider smashes protons together at enormous energies, hoping to produce particles that slip through detectors unseen but leave missing momentum behind. None have appeared yet, but the search continues. Because dark matter remains elusive, some physicists have explored alternatives that modify gravity instead of adding new matter. Ideas such as MOND, TVs, or FR gravity aim to explain galaxy motions without unseen mass. However, dark matter evidence comes from many independent sources: rotation curves, galaxy clusters, gravitational lensing, the cosmic microwave background, and the growth of structure, making it difficult for one theory of modified gravity to explain all of them at once. A few cases show partial success, but most researchers still find that a universe filled with dark matter fits the evidence best. While dark matter remains hidden, another mystery reshaped cosmology: dark energy. In the 1,990 seconds, two teams, led by Saul Perlmutter, Brian Schmidt, and Adam Rees, studied Type Ia supernovae, exploding stars of known brightness used as cosmic mile markers. They expected to see that the universe's expansion was slowing down under gravity. Instead, they found the opposite. Distant galaxies were receding faster than expected. The universe was speeding up. The simplest explanation is that empty space itself carries energy, a smooth pressure now known as dark energy. It makes up about 70% of the cosmos. while dark matter contributes roughly 25%, and everything we can see, stars, gas, dust, only about 5%. Dark energy behaves like Einstein's cosmological constant, a property of space that doesn't fade as the universe grows. But quantum physics complicates the story. Calculations of vacuum energy predict values 10 to the power of 120 times larger than what we observe. This mismatch, the greatest in all of science, hints that our theories are missing something profound. To visualize dark energy, imagine the universe as a loaf of raisin bread rising in the oven. As the dough expands, the raisin's galaxies move apart. Now imagine the oven's heat suddenly turns up. The dough balloons outward faster and faster. That runaway growth is what dark energy does to space. Because its density stays roughly constant, the more space there is, the more dark energy exists. The universe is not only expanding, it is accelerating. What happens next depends on how dark energy behaves. If it stays constant, expansion will continue forever. Distant galaxies will drift beyond our cosmic horizon until only our local group remains. But if dark energy grows stronger with time, expansion could spiral into the Big Rip, a future where galaxies, stars, planets, and even atoms are torn apart as space itself stretches beyond the strength of matter's forces. Some models suggest this could occur tens of billions of years from now. Others predict it will never happen at all. Meanwhile, the search for dark matter continues to evolve. Particle physicists are probing lighter axions, hypothetical particles proposed to fix puzzles in quantum theory. Using strong magnetic fields and exquisitely sensitive detectors, experiments like ADMX and new quantum cavity instruments listen for axions converting into faint radio waves. Elsewhere, telescopes scan for the glow of annihilating dark matter or the gravitational ripples of merging black holes that might be primordial. Even with no direct detection, the larger cosmic picture fits remarkably well. The LCDM model Lambda Cold Dark Matter has survived every major test. Patterns in the cosmic microwave background, the clustering of galaxies, and the motion of massive clusters all align with a universe dominated by cold, dark matter, and dark energy. Each new experiment narrows the possibilities, bringing us closer to understanding the invisible framework that shapes everything. For now, our best map of the cosmos says this: almost everything we see, every star, planet, and atom, is just the frosting on an unseen cosmic cake. The true ingredients of the universe, the forces that sculpt its structure and decide its fate, remain hidden in shadow, yet their fingerprints are everywhere in the bending of light, in the whisper of background radiation, and in the silent expansion of space itself. Step by step, as instruments sharpen and ideas evolve, we are tracing the outlines of that invisible architecture, moving closer to uncovering what the universe is truly made of. For much of the 20th century, astronomers wondered whether the universe would expand forever or someday fall back on itself. In its earliest moments, the cosmos was a contest between two forces: expansion and gravity. If gravity were strong enough, perhaps it could one day pull everything home again. This idea became known as the Big Crunch. In that version, dark energy either fades away or was never constant to begin with. Expansion would slow, stop, and reverse. Galaxies that had once drifted apart would begin to converge, drawn back through a shrinking cosmic web. Temperatures would climb as space contracted, and the night sky would grow brighter as galaxies collided. Eventually, everything matter, light, and space-time itself, might collapse into a single blazing point, an echo of the Big Bang in reverse. It's a beautifully symmetrical idea, the universe ending where it began. But observations disagree. The redshift of galaxies and the faint patterns in the cosmic microwave background tell us expansion is accelerating, not slowing. Unless dark energy changes dramatically, gravity will never reclaim control, and the Big Crunch will remain a poetic dream rather than our true destiny. That leaves another, quieter ending, the Big Freeze. This one is slow and silent, a long cosmic fading. If dark energy stays constant, as current evidence suggests, space will keep stretching forever. Galaxies will drift apart until they vanish beyond the cosmic horizon, too far for their light ever to reach us. In 100 billion years, the sky would already look emptier. In 1 trillion, nearly all other galaxies will be gone. By then, the Milky Way and Andromeda will have merged into a single, massive galaxy. A lonely island surrounded by darkness. Star formation will dwindle as gas runs out. The last new stars will ignite about 1 trillion years from now, marking the end of cosmic creation. One by one, the existing stars will burn through their fuel, and the universe will grow dimmer with every passing epoch. This era, sometimes called the degenerate era, will be ruled by the remnants of what once was: white dwarfs, neutron stars, and black holes. Red dwarfs, the small, faint, and long-lived stars, will shine for trillions of years, far beyond the current age of the cosmos. They will be the last true stars in a universe grown ancient, but even they will eventually die, fading into cold embers. The cosmos will then be filled with the corpses of creation, cooling white dwarfs, silent brown dwarfs, and the occasional black hole, still devouring matter that wanders too close. Time, however, does not stop. Over unimaginable stretches, 10, 40 years or more, white dwarfs will radiate their last warmth, becoming frozen black dwarfs. Neutron stars, unimaginably dense, will persist even longer, but even black holes, seemingly eternal, are not forever. Stephen Hawking showed that they emit faint radiation and slowly evaporate. A black hole with the mass of our sun would take around 1067 years to disappear, numbers so vast they dwarf the age of our 13.8 billion-year-old universe. When the last black hole evaporates, no stars or galaxies will remain. The universe will be a vast, dark sea filled only with scattered particles, electrons, positrons, perhaps a few protons drifting endlessly through expanding space. Temperatures will fall toward absolute zero, not because heat is turned off, but because there will be nothing left to make it. With no fusion, no gravity wells, and no collisions, the cosmos will slip into complete stillness. Even matter itself might not survive. Some theories predict that protons will eventually decay after about 1036 years, meaning every atom, every planet, every last grain of dust will crumble into radiation. What follows would be almost nothing at all, just a faint, fading background glow, the ghost of all that ever was. In this big freeze, the universe does not end in fire or collapse, but in silence. Space will continue to expand forever, yet with nothing left to change. Distances will grow meaningless. With no matter, there will be no here or there. The laws of physics will still exist, carved into the frozen fabric of space-time, but there will be no one to observe them, no mind left to wonder how it all began. Between the Big Crunch, the Big Rip, and the Big Freeze, our fate depends entirely on the true nature of dark energy, the invisible hand steering the universe's future. For now, the evidence favors the freeze, a cosmos that fades rather than falls. Still, every new measurement could change that story. The final destiny of everything from galaxies to atoms rests on a mystery we have only begun to glimpse, a whisper of energy shaping the grandest of all endings. The story of the universe may not end with a bang, but with silence, a vast, dark stillness stretching forever. The question of how everything ends, space, time, stars, and life, is one of science's most haunting mysteries. Every possible ending depends on one thing: how the expansion of space behaves. If expansion continues, slows, or reverses, it decides the fate of galaxies, matter, and energy alike. The Big Crunch is one of the oldest imagined endings. In this scenario, gravity eventually overcomes expansion. The universe stops growing, begins to contract, and galaxies fall back together. Over unimaginable ages, temperatures rise, distances shrink, and everything collapses into a single blazing point, a mirror of the Big Bang in reverse. Yet observations tell a different story. The expansion of the universe isn't slowing, it's speeding up. Unless dark energy changes in the distant future, the crunch remains only a poetic echo of what might have been. More unsettling possibilities arise from quantum physics. The universe might not be perfectly stable. It could exist in a false vacuum, a temporary state that only appears secure. One day, by random chance, a tiny bubble of true vacuum might form, expanding at the speed of light. It would rewrite the laws of physics as it spread, dissolving everything it touched: stars, atoms, and space itself. If such a transition ever occurs, there would be no warning and no escape. The universe would simply vanish into a new and alien reality. Beyond these catastrophic visions lies the idea of a multiverse, a cosmos filled with countless universes, each with different physical laws. In this picture, black holes might serve as gateways, birthing new universes as our own fades. The death of one cosmos could seed the birth of another. If so, existence itself might never end, only transform endlessly through cycles of creation and decay. For most cosmologists, though, the likeliest destiny is the Big Freeze, also called heat death. Here, the universe continues expanding forever. Galaxies drift apart, stars die, and energy spreads thinner and thinner. Eventually, the temperature of space falls so close to absolute zero that almost nothing happens. No light, no warmth, just a quiet sea of subatomic particles adrift in infinite cold. To us, such a future sounds hopeless. Life, after all, depends on energy. Stars provide nearly all the warmth and light that sustain living worlds. Without them, how could life endure? Yet some scientists suggest survival might still be possible, at least for a while. Advanced civilizations could tap the energy released near black holes or hoard the last reserves of matter and radiation. They might build vast machines to recycle and conserve energy, slowing their metabolism to stretch each pulse of heat over millennia. If any life survived that long, it would look nothing like life today. It might operate on chemistry we can't imagine, slow, efficient, and nearly immortal. Or perhaps intelligence would evolve beyond biology altogether, Information could become the new form of life, patterns of data or consciousness existing within quantum systems, living as pure thought in the dark. Some even dream that future civilizations might learn to escape this dying universe entirely. If the multiverse exists, perhaps they could open pathways to a new cosmos, rebooting creation in another realm. It sounds like science fiction, but so once did black holes and quantum fields. The will to survive might drive minds of the far future to bend the fabric of reality itself. Even before such extreme epochs, cosmic isolation will begin. As space expands faster and faster, galaxies will slip beyond our observable horizon, the limit beyond which light can never reach us. Communication will fade long before the end. No signal, no radio wave, not even the fastest beam of light will cross the widening void. Civilizations, if they exist in distant galaxies, will vanish from view forever. Each gravitationally bound cluster of galaxies will become its own cosmic island, cut off from the rest of creation. Within these islands, life and intelligence might persist for unimaginable ages, exploring, building, and remembering. But contact between islands will be lost. Knowledge, stories, and science will become local phenomena. The grand web of the cosmos will dissolve into isolated sparks, each burning alone in the dark. Perhaps those last civilizations will leave messages behind, monuments of thought carved into the matter of their galaxies, or signals cast into the void, knowing they will never be received. Or maybe they will turn inward, seeking meaning, not in connection, but in reflection. In the end, the struggle may not be to conquer the universe, but to preserve a fragment of wonder within it. And yet, there's beauty even in this ending. The universe began in light, grew rich with structure and life, and will fade into calm. Entropy wins, but it does so gracefully. The same laws that lit the stars also write their final elegy. When the last black hole evaporates and the final photon fades, the universe will not scream or burn. It will whisper into stillness. The fabric of space will stretch forever, cold and silent. But even then, the laws of physics will endure eternal, waiting, indifferent, etched into the empty geometry of space-time. There will be no eyes left to see, no minds left to wonder, yet the rules will remain, carved into nothingness itself. In that sense, the end of the universe is not just a story of death, but of endurance. Everything we know will vanish, but the order that shaped it all, the mathematics, the symmetry, the logic of existence, will persist in quiet permanence. The cosmos began as an explosion of light. It may end as a whisper of information, stretched thin across infinity. And in that whisper, perhaps, lies the faintest echo of everything that ever was.